A golf ball of mass 150 grams is hit horizontally from the top of a 40-metre high cliff with a speed of 25 metres per second. Using g equals 9.8 metres per second squared and ignoring air resistance, calculate the following values. So first thing we need to do is calculate the time that the ball takes to land. All right, what's the first thing we do? Draw a diagram. Excellent. So, and our diagram should have all of the information we know. So there is our golf ball. The mass of the golf ball is 150 grams. And it's a 40-metre high cliff. What else? Speed of 25 metres per second. Okay, so notice that it says the ball is hit horizontally. Okay, so our initial velocity is just 25 metres per second in the horizontal direction. We have no vertical velocity to begin with. Okay, so we need to take the time, or we need to calculate the time that the ball takes to land. All right, so a projectile is going to go something like this. We need to work out the time it takes to land. Now, remember I was saying before, whether you fire something horizontally or whether you drop it, it'll hit the ground at the same time because the acceleration is still the same. So all we need to consider at this point is the vertical direction. Okay? It doesn't matter. Our ball is going to travel with 25 metres per second in the horizontal direction forever. Okay? This value is not going to change. This 25 is not going to change. But it's the vertical direction that concerns us because we want to work out how long it takes the ball to get from the top of the cliff down to the ground. Okay? Horizontal distance doesn't matter. So, this is what I was saying before about SUVAT. We write down what we know and we write down what we want to know. Okay? So, just thinking about the vertical direction. We know the distance. How far does the ball have to travel in the vertical direction? 40 metres. So we know that our distance in the vertical direction is 40. We know our initial speed of the ball. In the vertical direction, what's the initial speed? Zero. There is no speed in the vertical direction, so our initial velocity is 0. We don't know our final velocity, and in fact we don't care. Our acceleration is what? 9.8. So this is where we might need to be a little bit careful. Whether we use 9.8 or negative 9.8, whether we decide down is positive or negative. In this case, since everything is moving down, let's say down is positive, and so then we don't need to worry about negatives. All right, so it's travelling 40 metres down, so it's travelling plus 40 metres, and it's travelling at it's accelerating at plus 9.8 metres per second squared. So we have 3 of those, and remember I was saying earlier, if you have any 3, you can work out any other one. And we want to work out, what do we want to calculate? Time. So we don't know time. And so what you would do is have a look at your SUVAT equations, and you need to find one that contains those 4 quantities. And if we have a look, which one? S equals ut plus a half at squared uses those 4. Notice we haven't used anything with v in it because we don't know v and we don't need to find v. Okay, we just need the equation that uses those 4 quantities. So let's use that one. S equals ut plus 1/2 at squared. All right, now we need to rearrange this a little bit because we're trying to solve for t. Now ut, straight away we know u is 0, so ut is also 0, so we can get rid of that. So we get s equals 1/2 at squared. If we rearrange a little bit, we get t is equal to 2s on a square root. So all I've done at this point, I've just rearranged it to get to that. Right, so t is equal to the square root of 2s on a, which is equal to the square root of 2 multiplied by, what's s, 40, divided by 9.8. So if someone could calculate that for me, that'd be great.
2.86.
So 2.87? 2.85? Yeah, something like that.
Yeah. Actually, 870 meters.
All right, no worries. So look, close enough depending on your rounding errors. So there, that's it. And remember, regardless of whether you've hit the ball at 25 meters per second or if you're just standing on the cliff and drop it, it's going to take the same amount of time to hit the ground because the acceleration downwards is exactly the same. Now it's different if you hit it upwards, then it will take longer than if you just dropped it. But if you're just hitting it horizontally, it'll take exactly the same amount of time to hit the ground. So this is the key with a Suvat equation. Write down what you know, write down what you want to know. Okay, and then find the appropriate equation and solve for your unknown. Calculate the distance that the ball travels from the base of the cliff, i.e. the range of the ball. Okay, so what we want to find out in this question, our ball is hit like that. We want to find the range, how far it has travelled. Okay, now this one's actually quite easy. It may not look it, but it is. Because there are a couple of assumptions we can use to make this more straightforward. How long is the ball in the air for? All right. 2.85 seconds. We know that's how long it takes to hit the ground. Okay. We know the initial speed. We know the initial speed of the ball is 25 meters per second in the horizontal direction. Now, if we know the time it's in the air and the speed in the horizontal direction, remember the speed in the horizontal direction doesn't change. So it starts off at 25 meters per second and its speed in the horizontal direction at the end is still 25 meters per second. We have a constant velocity. So therefore we don't need to use our Suvat equations. What do we use? Distance over time. So our velocity is equal to distance over time. And we want our distance. So distance is equal to time multiplied by velocity. 2.85 multiplied by 25. And I think if you calculate this, you'll work out that our golfer is not very good. Can't get a calculator working. There we are, 2.85. So you should get 71.25 meters. That's a disappointing golf shot. Top of a cliff, top of a 40-meter cliff, only managing to hit it 71 meters. That is disappointing. Okay. So, this is what we know. So when you're working out range or anything like that, it becomes a little bit easier because you can assume the horizontal distance is a constant. Okay, part C is where it gets a little bit trickier. Calculate the velocity of the ball as it lands. What do we need for velocity? Direction? Magnitude. All right. So if you look at our little diagram up there, our velocity is going to be in this direction. So we need to work out the magnitude of that vector as well as some way to describe the direction of it. Okay, so usually to describe the direction, you just do angle from the horizontal. Okay, it doesn't actually matter whether you do it from the horizontal or the vertical, but usually you go from horizontal. Okay, so let's draw this up. We want to work out our velocity. To find that, we need our two components. We need our vertical component at this point, and we need our horizontal component at this point. What is our horizontal component at that point? 25. Remember, the horizontal does not change. So that is 25 meters per second. So we need to work out that vertical component. Okay, to work out the vertical component, we have an acceleration, but it is constant. So we can use our Suvat equations. Okay, so that's just the same as our starting conditions that we did on the previous slide. We've got exactly the same starting conditions, except instead of solving for D this time, we're solving for, instead of solving for T, we're solving for V. So let's look at what we know and what we want to know. We know our initial speed is 0. We know our acceleration is 9.8. We know our distance is 40. If you wanted to, you could use the time you calculated earlier to work this out. Okay, so our time is 2.85. That's how long it's in the air for. And we want to know V. It's often nice when you've got the time to be able to use it because the equations are much nicer. V equals U plus AT. That's a nice looking equation. Very straightforward. So our final velocity in the vertical direction, so our initial velocity is 0 plus A is 9.8 multiplied by 2.85. $27.93. All right. So we've got in the vertical direction. So all of this is in the vertical direction. So by doing this, we can get the vertical component of the velocity. So we've got the horizontal, that hasn't changed, at 25 meters per second. But now we know that this over here is 27.93. So what's the easiest way to find the magnitude of V now? Pythag. Yeah, absolutely. Pythag. 27.93 squared plus 25 squared. Square root of that. So I get 37.48 meters per second. But we're not done. We've got the magnitude. What else do we need? We need our direction. So we need to work out that angle. How are we going to do that? Trig. Yep, you can either use cos or sine because we have, well, you could use tan as well if you wanted. Because we have everything there that we need. We've got all three sides. So, what do we want to use? Let's do sine. Sine theta equals O on H. So the sine of our angle is going to be 27.93 on 37.48. We just want the inverse sine of that. Now, as soon as I hit equals, the calculator died. Okay. So theta is the inverse sine of whatever that is, 0.7 something.